Hello there, and welcome to the Sleepy Library. Tonight, we are going on a gentle journey through one of science's most fascinating questions. Is teleportation possible? Can we really move from one place to another in the blink of an eye? Can you vanish from your living room and appear on a beach somewhere far away? It sounds like magic, doesn't it? Like something from movies and books, where heroes and wizards snap their fingers and whoosh, they're somewhere else entirely. But here's the wonderful thing about science. It takes ideas that sound impossible and asks, very carefully, very patiently, could this actually work? And the answer, as you'll discover tonight, is both simpler and stranger than you might imagine. So, settle in. Get comfortable. Let your mind wander through the world of particles and possibility. We're going to explore teleportation together, one gentle fact at a time. For as long as humans have existed, we have dreamed of moving faster. We walked, then we rode horses, then we built cars and trains and airplanes. Every step forward has been about getting from here to there more quickly, more easily. But no matter how fast we travel, we still have to cross the space in between. We still have to move through the world, 1 mile at a time, one step at a time. Teleportation promises something different. It promises to skip all that, to simply be in one place and then, without any journey in between, to be in another place. No waiting, no traveling, just instant movement. It's an idea that has captured imaginations for over 100 years. When science fiction writers first started dreaming about it, they imagined machines that could scan a person, break them down into tiny pieces, send that information somewhere else, and rebuild them perfectly at the other end. In the television show Star Trek, which started in the 1960s, characters would stand on a platform and say the famous words, "Beam me up." And then, with a shimmer of light and a special sound effect, they would disappear from one place and reappear on their spaceship. It looked so easy, so natural, as if the universe was just waiting for us to figure out how to do it. And that made people wonder, is this actually possible? Could we really do this someday? Scientists started thinking about it seriously, not just because it would be convenient, although it certainly would be. Imagine never having to sit in traffic again. Imagine visiting family on the other side of the world in an instant. Imagine being able to go anywhere you wanted, whenever you wanted, without any travel time at all. But scientists were interested in teleportation for a different reason. They wanted to understand the fundamental rules of the universe. They wanted to know if the laws of physics would allow such a thing to exist. And the more they studied, the more they discovered something surprising. Teleportation might actually be possible, just not in the way we imagined. The reality of teleportation, as it turns out, is both more limited and more interesting than the science fiction version. It doesn't involve stepping onto a platform and vanishing in a sparkle of light. It doesn't involve physically moving through space or breaking down your body into energy. Instead, it involves something much more subtle, something that happens at the tiniest scales imaginable, in the world of quantum mechanics, where the rules of everyday life stop applying. When most people think about teleportation, they picture a person standing in one place, and then suddenly, without warning, standing in another place. The person themselves, with all their thoughts and memories and feelings, moving from point A to point B, without crossing the space in between. But when scientists talk about teleportation, they mean something slightly different. They're talking about moving information, not matter. Let's think about what you're made of. You are made of atoms, trillions and trillions of atoms, all working together in incredibly complicated ways. These atoms are made of even smaller things called protons, neutrons, and electrons. And those are made of even tinier things called quarks. Everything in the universe is made of these incredibly small particles arranged in different patterns. Now, here's an interesting thought. What makes you, you? Is it the specific atoms in your body? Or is it the pattern, the arrangement, the information about how all those atoms are organized? If we could somehow scan every single atom in your body, record exactly where each one was and what it was doing, and then use that information to build an exact copy somewhere else, would that copy be you? This is where things get philosophical and a little bit strange. But it's also where the science of teleportation begins. Because what scientists have discovered is that we can teleport information. We can take the exact state of one tiny particle and make another particle somewhere else take on that exact same state. The particle itself doesn't travel, but the information, the pattern, the state of that particle can be moved instantly from one place to another. This is called quantum teleportation. And while it might not sound as exciting as beaming yourself to another planet, it's actually one of the most amazing discoveries in modern physics. It's real. It works. And scientists have been doing it in laboratories for over 30 years now. The story of quantum teleportation begins with a paper published in March of 1993. A group of 6 scientists from different countries worked together to figure out the mathematics of how teleportation could work using the strange rules of quantum mechanics. Their names were Charles Bennett, Gilles Brassard, Claude Crépeau, Richard Joser, Asher Perez, and William Wouters. Their paper had a long title that explained exactly what they had discovered. They showed that you could teleport an unknown quantum state using a combination of quantum entanglement and regular classical communication. It was just theory at first, just equations on paper, but it laid out the blueprint for how teleportation could actually happen. What made their discovery so important was that it found a way around a fundamental problem. In quantum mechanics, there's a principle called the uncertainty principle that says you can't measure everything about a particle at once. And there's another principle called the no-cloning theorem that says you can't make an exact copy of a quantum state. These two principles seem to make teleportation impossible. After all, if you can't measure all the information about a particle and you can't copy it, how could you possibly move it from one place to another? But Bennett and his colleagues found a clever solution. They discovered that by using entanglement, you could transfer a quantum state without ever measuring all of its properties and without making a copy. The original state would be destroyed in the process, but a perfect version would appear somewhere else. It was a beautiful piece of theoretical physics, and scientists around the world immediately wanted to try it in real experiments. To understand how quantum teleportation works, we need to talk about the quantum world. This is the world of things that are incredibly, incredibly small. Smaller than anything you can see with your eyes, even with a microscope. Smaller than a grain of sand. Smaller than a cell. Smaller than a molecule. We're talking about individual atoms and the particles inside them. In this tiny hidden world, the rules are different from the rules we experience in our everyday lives. Objects don't behave the way we expect them to. And that's because, at this incredibly small scale, the universe follows a different set of instructions. These instructions are called quantum mechanics, and they were discovered about 100 years ago by scientists who were trying to understand how atoms work. The story of quantum mechanics is one of the most fascinating chapters in the history of science. It began in the early 1900s, when scientists noticed something strange about light and energy. They found that energy didn't come in smooth, continuous amounts. Instead, it came in tiny packets, which they called quanta. This was shocking, because everything in classical physics suggested that energy should be smooth and continuous, like water flowing from a tap. But experiments showed that at the atomic level, energy comes in discrete chunks, like individual drops. Max Planck was one of the first scientists to realize this in 1900. He was studying how hot objects glow and emit light, and he found that he could only explain the results if he assumed energy came in these tiny packets. He thought this was just a mathematical trick, not a real feature of nature. But it turned out to be profoundly real. Albert Einstein built on this idea in 1905, when he explained something called the photoelectric effect, showing that light itself comes in particles, which we now call photons. For this work, Einstein won the Nobel Prize in Physics in 1921. As scientists continued to explore the atomic world, they found more and more strange things. Niels Bohr developed a model of the atom where electrons could only exist in specific orbits, jumping from one orbit to another in sudden leaps rather than sliding smoothly. Louis de Broglie suggested in 1924 that particles like electrons might also behave like waves, a crazy idea that turned out to be absolutely true. Erwin Schrödinger wrote an equation in 1926 that describes how these quantum waves behave, an equation that's still used today to calculate everything from the behavior of electrons in computer chips to the properties of molecules in your body. Werner Heisenberg developed a different approach to quantum mechanics at the same time, using matrices and mathematical tools that looked completely different from Schrödinger's wave equation. But remarkably, both approaches gave the same predictions. They were just different mathematical languages describing the same underlying reality. Heisenberg also discovered the uncertainty principle, that fundamental limit on what we can know about quantum particles. All of these discoveries came together in the 1920s and 30s to form what we now call quantum mechanics. It was a revolution in physics, completely changing how we understand the microscopic world. And it was controversial. Many scientists, including some of the founders of quantum mechanics themselves, were uncomfortable with how strange and probabilistic the quantum world turned out to be. Einstein, Bohr, Heisenberg, Schrödinger, and many others spent decades debating what quantum mechanics really meant, what it was telling us about reality. Those debates continue in some form even today. But despite the philosophical puzzles, quantum mechanics works. It makes predictions that match experiments with incredible precision. It's been tested millions of times in millions of different ways, and it always gives the right answer. Modern technology, from smartphones to lasers to medical imaging devices, all depends on quantum mechanics. We use it every day, even if we don't realize it. And one of the strangest predictions of quantum mechanics, one that took decades to verify experimentally, is quantum entanglement. In the everyday world, things are definite. A ball is either in your hand or it's not. A light is either on or it's off. A cat is either awake or asleep. But in the quantum world, things can be in multiple states at the same time. An electron can be spinning in one direction and the opposite direction simultaneously. A particle can be in two places at once. This sounds impossible, and in our everyday experience, it is impossible. But at the quantum level, it's just how things work. This strange property is called superposition. It means that before you measure or observe a quantum particle, it exists in all possible states at the same time. It's only when you look at it, when you measure it, that it collapses into one specific state. Before you check, the particle is doing everything. After you check, it's doing just one thing. Another strange rule of the quantum world is that you can't know everything about a particle at the same time. This is called the Heisenberg uncertainty principle, named after the scientist Werner Heisenberg who discovered it. It says that if you measure exactly where a particle is, you can't know exactly how fast it's moving. And if you measure exactly how fast it's moving, you can't know exactly where it is. The more precisely you know one thing, the less precisely you can know the other. This isn't because our measuring tools aren't good enough. It's a fundamental law of the universe. The quantum world has built-in fuzziness, built-in uncertainty. And that uncertainty is part of what makes quantum teleportation both possible and limited. Werner Heisenberg discovered this principle in 1927, when he was just 25 years old. He was trying to understand how electrons behave inside atoms, and he realized that there was something strange happening when you tried to measure them. The act of measuring changes what you're trying to measure. It's not that we're being clumsy or that our instruments are disturbing things. It's that at the quantum level, measurement itself changes reality. Before you measure, the particle exists in all possible states. After you measure, it's locked into one specific state, and you can never know what it was doing before you looked. This idea troubled many scientists, including Einstein. It seemed too strange, too uncertain, too random. Einstein famously said that God does not play dice with the universe. He believed there must be hidden information we simply couldn't access, something that would make the quantum world predictable again, if only we could see it. But experiment after experiment has shown that Einstein was wrong about this. The quantum world really is uncertain, really is probabilistic, really does change when you observe it. There are no hidden instructions. The fuzziness is real and fundamental. But the strangest, most wonderful property of the quantum world is something called entanglement. This is the key to quantum teleportation, and it's so strange that even Albert Einstein, one of the greatest scientists who ever lived, found it hard to believe. He famously called it spooky action at a distance. Here's how entanglement works. Imagine you have two particles, maybe two electrons, or two particles of light called photons. You create them together in a special way so that they become connected, linked, entangled. Once they're entangled, something remarkable happens. No matter how far apart these particles get, no matter if they're separated by an inch or a million miles, they remain connected in a deep, fundamental way. If you measure something about one particle, the other particle instantly knows what happened. If you measure the spin of one electron and find it spinning up, the other electron will instantly be spinning down. If you check the state of one photon, the other photon takes on the corresponding opposite state. Instantly. Not after a delay. Not after information travels from one to the other at the speed of light. Instantly. This sounds like it shouldn't be possible. After all, nothing can travel faster than light. That's one of the most important rules in physics, established by Einstein himself in his theory of relativity. But entanglement doesn't break this rule. That's because no information is actually traveling between the particles. Instead, the particles share a single quantum state. They're not two separate things that communicate with each other. They're one system spread across space. Think of it like this. Imagine you have a coin that you split perfectly in half. You keep one half and send the other half to your friend on the other side of the world. When you look at your half and see heads, you instantly know that your friend's half shows tails. No information traveled. You didn't send a message. but the two halves were always connected, always parts of the same coin, so knowing about one tells you about the other. Entanglement is like that, except much stranger. Because in the quantum world, before you look, both halves are showing heads and tails at the same time. It's only when you look at one that they both suddenly decide what they're showing. And they always decide together, instantly, no matter how far apart they are. Scientists doubted this for a long time. Einstein thought there must be hidden information that we just couldn't see. He thought the particles must have already decided what they were doing before we looked, and we just didn't know it yet. But starting in the 1960s, scientists began doing experiments to test this, and every experiment showed the same thing. Entanglement is real. The particles really are connected in this spooky, instantaneous way. There are no hidden instructions. The quantum world really is this strange. In 2022, 3 scientists won the Nobel Prize in Physics for their work proving that entanglement is real and for showing how we can use it. Their experiments settled the question once and for all. Entanglement is not just a theory, it's a fact about how our universe works. The 3 scientists who won this prize were Alain Aspect from France, John Clauser from the United States, and Anton Zeilinger from Austria. Each of them conducted careful experiments over many decades to test whether entanglement was real, or whether Einstein was right that there must be hidden information. They used photons, particles of light, and measured their properties in different ways. They set up experiments where the measurements happened so far apart and so quickly that no information could possibly travel between them, even at the speed of light. And every single time, the particles behaved as if they were connected, as if they knew what was happening to their partner instantly. These experiments used something called Bell's theorem, named after physicist John Stuart Bell. In 1964, Bell figured out a mathematical test that could distinguish between Einstein's idea of hidden information and the quantum mechanical idea of true entanglement. If Einstein was right, certain measurements would give one range of results. If quantum mechanics was right, the results would be different. When scientists finally did these experiments in the 1970s and 80s and continued refining them through the decades, the results always matched quantum mechanics, not Einstein's theory. The universe really does have this spooky action at a distance. Understanding entanglement changed everything for physics. It opened up new possibilities that nobody had imagined before. It led to ideas about quantum computers, quantum communication, and of course, quantum teleportation. Without entanglement, none of these things would be possible. Entanglement is the key that unlocks all these quantum technologies. Now we can finally talk about how quantum teleportation actually works. It's a process that uses entanglement to move information from one place to another. Let's walk through it step by step, slowly and gently. Imagine we have 2 people. Scientists always call them Alice and Bob. Alice wants to send quantum information to Bob. Maybe she has a particle, let's say a photon, and she wants Bob to have a particle in the exact same state. The exact same quantum state, with all the same properties and characteristics. First, Alice and Bob need a pair of entangled particles. They create 2 photons that are entangled with each other. Alice keeps one of these entangled photons, and Bob takes the other one far away. Maybe to another room, maybe to another building, maybe to another city. The distance doesn't matter because the photons are entangled. Now Alice has 2 photons. She has the original photon that she wants to teleport, the one whose state she wants to send to Bob. And she has her half of the entangled pair. Bob has the other half of the entangled pair. Next, Alice does something clever. She takes her original photon and her half of the entangled pair and performs a special kind of measurement on both of them together. This measurement is called a Bell state measurement, named after the physicist John Bell, who helped us understand entanglement. This measurement entangles her original photon with her half of the entangled pair. Here's where the magic happens. Because of how entanglement works, when Alice performs this measurement, something changes about Bob's photon too. Even though it's far away, even though nothing had traveled between them, Bob's photon changes. It doesn't yet have the same state as Alice's original photon, but it's close. It's almost there. The information has started to transfer. But there's a catch. The measurement that Alice performs gives her one of 4 possible results. It's random. She doesn't know which result she'll get until she does it. And depending on which result she gets, Bob needs to do different things to his photon to complete the teleportation. So Alice does one more thing. She uses normal communication, maybe a phone call or an email or a radio signal, to tell Bob which result she got. This information travels at the speed of light, just like any normal message. It's not instantaneous, but it's necessary. When Bob receives Alice's message, he knows what to do. Depending on which result Alice got, he might need to flip his photon state, or rotate it, or leave it alone. He performs the right operation, and suddenly his photon is in the exact same state that Alice's original photon was in. The quantum information has been teleported from Alice to Bob. But here's something important to understand. Alice's original photon is no longer in that state. The measurement she performed changed it. The original information was destroyed in the process of teleporting it. This might sound like a problem, but it's actually necessary. There's a rule in quantum mechanics called the no-cloning theorem, which says you cannot make an exact copy of a quantum state. You can't duplicate quantum information. You can only move it from one place to another. This is different from normal information, like copying a file on a computer. With quantum information, there can only be one copy. When you teleport it, the original disappears, and a perfect copy appears somewhere else. It's like the universe has a strict policy about duplication. The process of quantum teleportation is sometimes described using a simple analogy. Imagine you want to send a message written in an unknown language that you can't read. You don't know what the message says, and you're not allowed to try to translate it or copy it. But you do have a special telephone line that's connected to your friend in a magical way. You perform a measurement on your message and your special telephone, and then you tell your friend the result of that measurement using a regular phone call. Your friend uses that information to recreate the exact message on their end, even though neither of you ever knew what the message actually said. That's similar to how quantum teleportation works, except instead of messages, we're dealing with quantum states, and instead of a magical telephone line, we're using quantum entanglement. The mathematics behind quantum teleportation is quite complex, involving what physicists call Hilbert spaces and tensor products and unitary transformations. But the basic idea is surprisingly simple. You use entanglement to create a connection between two places. You perform a special measurement that transfers information through that connection, and you complete the transfer by sending some classical information. The beauty is that you never need to know what quantum state you're teleporting. You never need to measure all of its properties. You just follow the steps, and the quantum state appears at the destination. So that's how quantum teleportation works in theory. But what about in practice? What have scientists actually managed to teleport so far? The first successful quantum teleportation experiment happened in 1997. A team of scientists at the University of Innsbruck in Austria managed to teleport the quantum state of a photon, a particle of light. The photon itself didn't move, but its quantum state was successfully transferred to another photon. It was a historic moment. The idea that had been just mathematics on paper was now real. Quantum teleportation worked. Since then, scientists have gotten better and better at it. They've teleported the quantum states of many different things. They've teleported photons over longer and longer distances. They've teleported the states of atoms, electrons, and even small groups of particles working together. In 2004, scientists in Austria teleported quantum information over 600 meters across the Danube River in Vienna. They used fiber optic cables, the same kind of cables that carry internet data. In 2012, scientists in China teleported the quantum state of photons over 97 kilometers, which is over 60 miles. They did this through the air, sending the photons through the atmosphere. But the most impressive distance record came in 2017. Scientists in China used a satellite called Michius to teleport quantum information from the ground all the way up to the satellite in space. The distance was about 1,400 kilometers, which is almost 900 miles. The photons traveled through the atmosphere and out into space, and the quantum information arrived safely. This was a huge achievement. It showed that quantum teleportation can work over very long distances, even through challenging conditions like the Earth's atmosphere. It opened up the possibility of creating a quantum internet, a network of quantum communication that could span the entire planet and maybe even reach other planets someday. Scientists have also been improving the success rate. Early quantum teleportation experiments only worked sometimes. They were probabilistic, meaning there was a chance they would fail. But more recent experiments have achieved what's called deterministic teleportation. This means it works every single time you try it, as long as everything is set up correctly. In December 2024, scientists at Northwestern University achieved something remarkable. They managed to teleport quantum information through regular fiber optic cables that were already carrying normal internet traffic. Imagine millions of data packets zooming through a cable, and somehow, delicate quantum states were able to pass through that busy highway without getting disturbed. It's like riding a bicycle safely through a tunnel full of speeding trucks. This breakthrough means quantum teleportation might be able to use existing infrastructure, which would make it much easier and cheaper to build quantum networks. But here's what's important to remember. All of these experiments have teleported information. The quantum state of a particle, not the particle itself, and certainly not anything larger. Not a molecule, not a cell, not an object, and not a person. The physical matter stays where it is. Only the information, the pattern, the quantum state gets teleported. These experiments have also taught us a lot about how to work with quantum information. Scientists have learned how to create entangled particles more reliably. They've learned how to keep quantum states stable for longer periods of time. They've learned how to measure quantum properties without completely destroying them. They've learned how to send quantum information through noisy environments like the atmosphere or busy fiber optic cables. Each experiment builds on the ones before it, adding new techniques, solving new problems, pushing the boundaries of what's possible. One interesting development has been the teleportation of more complex quantum states. Early experiments teleported very simple states, like whether a photon was polarized horizontally or vertically. But more recent experiments have teleported more complicated states that involve multiple properties at once. In 2015, scientists in China managed to teleport what's called multiple degrees of freedom, meaning they teleported several different properties of a particle all at the same time. This is important because real quantum information, the kind we might want to use in quantum computers, is often very complex. Scientists have also been working on making quantum teleportation more practical and reliable. Early experiments required very precise timing, very careful alignment of equipment, and they only worked some of the time. If the entangled particles weren't perfectly prepared, or if there was any noise or interference, the teleportation would fail. But newer experiments have achieved what's called deterministic teleportation, where the process works every single time as long as the setup is correct. This is crucial for building real quantum technologies that people can actually use. Another important development has been quantum teleportation between different types of systems. Scientists have teleported quantum states from photons to atoms, from atoms to ions, from one type of particle to another. This is important because different quantum systems are good for different things. Photons are great for sending information over long distances, but they're hard to store. Atoms can store quantum information for a long time, but they're hard to move around. By being able to teleport quantum states between different types of particles, scientists can combine the strengths of different systems. So that raises the big question. If we can teleport the quantum states of tiny particles, can we scale up? Can we eventually teleport larger things? Could we teleport a grain of sand, a paperclip, a book, a person? The short answer is that it's incredibly, unimaginably difficult. So difficult that most scientists think it will never be possible. At least, not in any practical way. Here's why. Think about how many atoms are in your body. The number is so large, it's hard to even comprehend. There are approximately 10 to the power of 27 atoms in a human body. That's a 1 followed by 27 zeros. 10,000 trillion atoms. Each one of these atoms is made of smaller particles like electrons, protons, and neutrons. And each of these particles has its own quantum state that would need to be measured and teleported. Even measuring all these quantum states is impossibly hard. Remember the Heisenberg uncertainty principle. It says you can't know everything about a quantum particle at the same time. The more precisely you measure one property, the less precisely you know others. To perfectly reconstruct a person, you would need to know the exact quantum state of every single particle in their body. But the uncertainty principle makes this fundamentally impossible. There will always be some fuzziness, some uncertainty, some information you simply cannot get. And even if you could somehow measure all this information, which would take more computing power than exists in the entire world, you would then need to send it somewhere. The amount of data would be staggering, completely overwhelming. It would take longer than the age of the universe to transmit all that information using any technology we can imagine. Then, even if you could send all that information, you would need to have all the right atoms waiting at the destination, ready to be arranged in exactly the right pattern. Where would these atoms come from? How would you get them? And how would you arrange them perfectly, down to the quantum level, to rebuild the person? And remember, quantum states are incredibly delicate. They're fragile. They can be disturbed by the tiniest things: heat, light, vibrations, stray magnetic fields. All of these can cause what's called decoherence, where the quantum state falls apart and loses its quantum properties. Keeping the quantum states of trillions of particles stable and coherent, while trying to teleport them all, would be essentially impossible. To understand just how delicate quantum states are, consider this. Scientists working with single qubits in quantum computers have to work incredibly hard to keep those qubits stable for just a fraction of a second. They cool their systems down to within a tiny fraction of a degree above absolute zero. They shield them from electromagnetic radiation. They isolate them from vibrations. And even with all this effort, qubits still lose their quantum properties after a short time. Now imagine trying to do this not for 1 qubit, but for 10 to the power of 28 qubits, all at the same time, all needing to stay coherent throughout the entire scanning, transmission, and reconstruction process. It's not just difficult, it's absurdly, impossibly difficult. The timescales involved make it even worse. Let's say you could somehow scan one atom every nanosecond, which is a billionth of a second. That's incredibly fast, far faster than any technology we have. Even at that impossible speed, scanning all the atoms in your body would take about 30,000 years. And during those 30,000 years, every atom you'd already scanned would be constantly losing its quantum coherence, constantly being disturbed by the environment, constantly changing. By the time you finished scanning, the first atoms you scanned would have long since lost their quantum states. You might think, well, what if we scan everything at once? But that would require having a scanner large enough and precise enough to simultaneously measure the quantum state of every atom in your body. The energy requirements alone would be staggering. Every measurement requires energy. Measuring the quantum state of a single atom might not take much energy, but measuring 10 to the power of 27 atoms would require enormous amounts. And that's just for the measurement. Transmitting all that information would require even more energy. And reconstructing a person from all those quantum states would require energy again, because you'd need to arrange atoms precisely, fight against entropy, overcome binding energy, and create all the complex structures of a living organism. Some scientists have tried to estimate how much energy it would take to teleport a person in the style of science fiction. The numbers are mind-boggling. One estimate suggests it would take more energy than the entire sun produces in a year. Another estimate suggests it would take more energy than all the stars in a galaxy produce in their entire lifetimes. These aren't exact calculations, because we don't really know how such a process would work, but they give you a sense of the scale. The amount of energy required isn't just beyond our current technology, it's beyond anything we could imagine being practical, ever. There's another problem too: energy. Moving all this information and rebuilding a person would require enormous amounts of energy. Some scientists have calculated that teleporting a human being in the way we see in science fiction would require more energy than all the stars in a galaxy produce. That's not just difficult, that's physically impractical, on a scale we can barely imagine. And we haven't even talked about what would happen if something went wrong. What if there was an error in the transmission? What if one quantum state got corrupted? In a quantum computer, an error might give you the wrong answer to a calculation. Annoying, but not catastrophic. But in teleporting a person, an error could mean missing atoms, misplaced molecules, proteins that don't fold correctly, neurons that aren't connected right. The result could be anything from minor imperfections to complete disaster. And remember, you can't do a test run. You can't teleport a person and keep the original around to compare, because the original is destroyed as part of the process. You only get one chance to get it right. This is why most scientists think human teleportation will never be practical, even if it's not strictly impossible according to the laws of physics. The technical challenges are just too enormous. The energy requirements are too extreme. The complexity is too overwhelming. The risks are too great. It's the kind of problem where every time you solve one challenge, you discover 10 more challenges hiding behind it. But perhaps the biggest obstacle is something even deeper. Even if we could overcome all these technical challenges, even if we somehow had infinite computing power and infinite energy and perfect control over quantum states, there's a philosophical question we need to ask. If you scan every atom in a person's body, destroy the original, and rebuild an exact copy somewhere else, Is it the same person? The copy would have all the same memories, the same thoughts, the same personality. They would think they were you. They would feel like they were you. They would have all your relationships and all your experiences. But is it truly you? Or is it a copy of you, while the original you was destroyed in the scanning process? This is sometimes called the teleportation paradox, or the problem of personal identity. Science can't answer this question because it's not really a scientific question. It's a question about consciousness, about what makes you you. Different people might have different answers. Some might say the copy is you because it's identical in every way. Others might say the original you ceased to exist when it was scanned and destroyed, and what arrives at the destination is a new person, even if they're identical. This isn't just a thought experiment. If human teleportation ever became real, we would need to think carefully about these questions. Would a teleported person have the same rights as before? Would they still be married to their spouse? Would they still own their house? Would they still be responsible for their past actions? These aren't just philosophical puzzles. They're real ethical questions that would need real answers. Some philosophers have thought about this problem for a long time. There's an ancient puzzle called the Ship of Theseus that asks a similar question. If you have a wooden ship, and over many years you replace every single plank, every nail, every piece of rope, until not a single original part remains, is it still the same ship? Most people feel like yes, it's still the same ship because it has the same form, the same function, the same history. But what if you took all the old parts and built a second ship out of them? Now, which one is the original ship? The one that kept the same form, or the one made of the original materials? Teleportation creates an even stranger version of this puzzle, because in teleportation, you would be destroying the original and building a copy. The copy might be perfect down to every last atom, but it's still a copy. Some people might say this doesn't matter. If the copy is identical, then for all practical purposes, it is you. Your memories continue, your personality continues, your relationships continue. What else could possibly matter? But other people might feel deeply uncomfortable with this. They might feel that the original person, the continuous thread of consciousness and experience, ends when the scanning and destruction happens. The person who appears at the destination might be identical, might even feel like they're the same person, but they would actually be a new being, a copy, not the original. This question becomes even more complex when you consider consciousness. We don't really understand what consciousness is or how it works. Is consciousness just the pattern of information in your brain? Or is it something more? Something that depends on the continuous physical existence of your neurons? If we teleport your brain's information to new atoms, does your consciousness go with it? Or does it end, leaving behind a new consciousness that thinks it's you? These aren't questions science can answer, because they're not really about physics. They're about philosophy, about the nature of identity and self. Different people have different intuitions about what the right answer is, and there may not be one correct answer that everyone agrees on. Even though teleporting people seems impossible, quantum teleportation still has an incredible future ahead of it. The ability to teleport quantum information is already changing technology in important ways. One of the most exciting applications is quantum computing. Quantum computers use quantum bits, called qubits, instead of regular bits. While a regular bit can only be 0 or 1, a qubit can be both at the same time, thanks to superposition. This allows quantum computers to perform certain calculations much faster than regular computers could ever manage. But quantum computers face a problem. Qubits are incredibly delicate. they lose their quantum properties very easily. Quantum teleportation can help solve this problem. If a qubit becomes corrupted or unstable, scientists can use teleportation to transfer its state to a fresh, stable qubit. This helps quantum computers stay accurate and reliable. The problem of keeping qubits stable is one of the biggest challenges in building practical quantum computers. Qubits need to maintain their quantum state long enough to perform calculations, but they're constantly being disturbed by their environment. Heat causes atoms to vibrate, which disturbs quantum states. Stray electromagnetic fields can flip qubits into the wrong state. Even cosmic rays from space can occasionally hit a quantum computer and cause errors. This is why quantum computers need to be kept at incredibly cold temperatures, often colder than outer space, and shielded from electromagnetic interference. But even with all these precautions, errors still happen. This is where quantum error correction comes in. Just like regular computers have error correction codes to fix bits that get flipped accidentally, quantum computers need quantum error correction to fix qubits that become corrupted. But quantum error correction is much harder than classical error correction, because you can't just copy a qubit to make a backup. Remember the no-cloning theorem. You can't duplicate an unknown quantum state. What you can do is spread the information from one qubit across multiple qubits in a clever way, so that if one qubit gets corrupted, you can recover the information from the others. And quantum teleportation plays a crucial role in this process. When you detect that a qubit has been corrupted, you can use teleportation to move its quantum state to a fresh, uncorrupted qubit. This allows the quantum computer to correct errors without losing the quantum information it's trying to process. Some researchers are also exploring how quantum teleportation could help connect multiple small quantum computers together to create a larger, more powerful quantum computer. Right now, the biggest quantum computers have a few hundred qubits. But to solve really interesting problems, we might need quantum computers with millions or billions of qubits. Building a single quantum computer that large might be extremely difficult. But if we could build several smaller quantum computers and connect them using quantum teleportation, we could effectively create a larger quantum computer distributed across multiple locations. The quantum teleportation would allow qubits in different locations to interact as if they were in the same computer. This distributed approach to quantum computing could also make quantum computers more fault-tolerant. If one module fails, the others could continue working. And it would allow quantum computers to be upgraded more easily. Instead of replacing an entire quantum computer when better technology becomes available, you could just swap out individual modules while keeping the network running. Quantum computers promise to revolutionize many fields. They could help design new medicines by simulating how molecules interact with incredible precision. They could help develop new materials with properties we can only dream of. They could solve optimization problems that would take regular computers longer than the age of the universe. They could help us understand complex systems like climate, traffic flow, and financial markets. They could break the encryption that currently protects our digital communications, which is why we need quantum communication to protect against quantum computers. And quantum teleportation is essential to making all of this possible. Quantum teleportation is also essential for building quantum networks. Just like the internet connects computers all over the world, a quantum internet would connect quantum computers and quantum communication devices. Information sent over a quantum network would be perfectly secure. If anyone tried to intercept or eavesdrop on the quantum information, the quantum states would be disturbed, and everyone would know immediately. This kind of security is impossible with regular communication. With normal internet traffic, a clever hacker can intercept your data without you knowing. They can make a copy of your message while it's traveling through cables or through the air, read it, and send it on its way, and you would never know they were there. But with quantum communication, using entanglement and teleportation, the laws of physics themselves protect your information. Any attempt to spy on the message would destroy it. This is because of the principle that measuring a quantum state changes it. If someone tries to measure the quantum states traveling through a quantum network, those measurements would disturb the states, and the disturbance would be noticeable at both ends. It's like having an envelope that crumbles into dust the moment anyone but the intended recipient tries to open it. This property makes quantum communication incredibly valuable for things like banking, government communications, military applications, and any situation where security is critical. Several countries are already investing heavily in quantum communication technology. China has launched quantum communication satellites and built quantum networks connecting major cities. The European Union has a program called the Quantum Internet Alliance, working to build quantum networks across Europe. In the United States, the Department of Energy has plans for a quantum internet connecting national laboratories. These are early steps, but they show that quantum communication is moving from laboratory experiments to real-world infrastructure. Banks are interested in quantum communication because they need to send financial information securely. Governments are interested because they need to protect classified information. Companies are interested because they need to protect trade secrets and customer data. As quantum computers become more powerful, they'll be able to break many of the encryption methods we currently use to protect regular internet traffic. But quantum communication, protected by the laws of physics rather than mathematical complexity, would remain secure even against quantum computers. Quantum teleportation might also help us build better sensors and measurement devices. Because quantum states are so sensitive, they can detect incredibly tiny changes in things like magnetic fields, gravity, or temperature. By using entanglement and teleportation, scientists can create sensors that are more precise than anything possible with regular technology. These could be used in medical imaging, geological surveys, or even searching for gravitational waves in space. For example, quantum sensors could detect tiny variations in Earth's magnetic field that might indicate underground mineral deposits or geological structures. They could measure minute changes in gravity that reveal the shape and density of underground formations, helping geologists understand what's beneath the surface without having to drill. In medicine, quantum sensors might be able to detect the incredibly weak magnetic fields produced by nerve cells in the brain, giving doctors new ways to diagnose and treat neurological conditions. In space, quantum sensors could detect gravitational waves with much greater sensitivity than current detectors, helping astronomers learn about colliding black holes, neutron stars, and other extreme events in the universe. Scientists are already building quantum sensors for these applications. They use entangled particles to make measurements that would be impossible with regular sensors. The entanglement allows them to cancel out certain types of noise and interference, leaving only the signal they're trying to detect. Quantum teleportation could help distribute the entangled particles needed for these sensors, making it easier to build quantum sensor networks covering large areas. Another possible application is in space exploration. Imagine a future where we've sent equipment to Mars or to the moons of Jupiter. Instead of sending physical objects back and forth, which takes months or years, we could use quantum teleportation to send information instantly. Granted, we would still need to set up entangled particles in advance, and we would need to send classical information which travels at the speed of light. But even with these limitations, quantum communication could make exploring the solar system easier and more efficient. Quantum teleportation could also revolutionize how we think about data storage and transmission. Right now, when we store information in computers or send it over the internet, we use regular bits that are either 0 or 1. But quantum information is much richer. A qubit can be in a superposition of 0 and 1, containing more information in a single particle than a classical bit ever could. By using quantum teleportation, we could create quantum memory systems that store vast amounts of information in very small spaces. We could create quantum communication networks that transmit information with perfect security and incredible efficiency. Scientists are also exploring how quantum teleportation might help us understand the universe better. There are deep connections between quantum entanglement and other areas of physics, like black holes and the nature of space-time itself. Some theoretical physicists think that entanglement might be connected to wormholes, those hypothetical tunnels through space and time. In 2022, scientists used a quantum computer to simulate a tiny wormhole and showed that information could pass through it in a way that looked a lot like quantum teleportation. This doesn't mean we can build real wormholes or travel through them, but it suggests that entanglement and the structure of space-time might be connected in fundamental ways we're only beginning to understand. There are also potential applications in fundamental science research. Quantum teleportation could help us create more precise measurement devices for detecting things like gravitational waves, which are ripples in space-time caused by massive events like colliding black holes. It could help us build better atomic clocks that keep time more accurately than any clock that exists today. It could help us test the fundamental laws of physics in new ways, looking for tiny deviations that might tell us about new physics beyond what we currently understand. But we need to be honest about what quantum teleportation cannot do. It cannot send information faster than light. This is important because one of the most important rules in physics, established by Einstein's theory of relativity, is that nothing can travel faster than light. Not matter, not energy, and not information. At first glance, quantum entanglement seems like it might break this rule. After all, when you measure one entangled particle, the other particle instantly changes, no matter how far away it is. Instantly means faster than light, doesn't it? But here's the subtle point. When you measure your entangled particle, you get a random result. You might get spin up or spin down, but you can't control which one you get. And when the other particle changes, it changes to match your random result. But the person holding the other particle doesn't know what result you got until you tell them using normal communication, which travels at the speed of light. So even though the quantum state changes instantly, no information actually travels faster than light. You can't use entanglement to send a message faster than light, because the results are random and meaningless until they're compared with classical information sent the normal way. This means quantum teleportation, even in its most advanced form, would always require some kind of slower-than-light communication. You can't teleport information completely instantly. There will always be a delay, even if it's very short. Another limitation is that quantum teleportation only works for quantum information. It doesn't transport matter or energy. It only transports the pattern, the state, the information about how particles are arranged. If you wanted to teleport an object, you would need to have all the atoms of that object already waiting at the destination. You're not creating matter out of nothing, you're just rearranging matter that's already there. This is very different from science fiction teleportation, where people simply vanish from one place and appear in another. In quantum teleportation, the matter doesn't move, only information moves. To teleport a person, you would need to have all the atoms needed to build a person already waiting at the destination. and you would need to have them arranged in roughly the right pattern before you could even start the teleportation process. So while quantum teleportation is real and working in laboratories around the world, it's not the magical instant transportation device we imagine. It's something more subtle, more limited, but in its own way, just as remarkable. There are other fundamental limits as well. Quantum states are incredibly fragile. They can be disturbed by the tiniest things. Even a single photon of stray light hitting a particle can collapse its quantum state. Temperature causes atoms to vibrate and jiggle, which disturbs quantum states. Magnetic fields, electric fields, cosmic rays passing through the atmosphere, all of these can cause what's called decoherence, where a quantum state loses its quantum properties and becomes classical. This is why quantum experiments need to be done in extremely controlled environments, often at temperatures close to absolute zero, in vacuum chambers that block out all external influences. For macroscopic objects, decoherence happens almost instantly. The quantum states that exist inside the atoms of your body are constantly being measured and disturbed by all the other atoms around them, by the light hitting you, by the heat, by everything. This is why you don't experience quantum superposition in everyday life. This is why you're never in two places at once, why you can't walk through walls, why the quantum weirdness stays hidden at the level of individual particles. The larger something gets, the faster it loses its quantum properties. For something as large as a person, quantum coherence would last for an unimaginably tiny fraction of a second. This makes teleporting anything macroscopic essentially impossible with any technology we can imagine. There's also the problem of what physicists call the no-cloning theorem. This theorem, proved mathematically in 1982, says that you cannot make an exact copy of an arbitrary unknown quantum state. You can move it from one place to another, which is what teleportation does, but you can't duplicate it. This has important implications for quantum information and quantum computing, because it means quantum information is fundamentally different from classical information. With classical information, you can copy it as many times as you want, but quantum information can only exist in one place at a time. This theorem is actually what makes quantum teleportation possible in the first place. Because the original quantum state is destroyed during teleportation, we're not making a copy, we're moving the state. If we could make perfect copies of quantum states, then quantum teleportation wouldn't be necessary. But because we can't, teleportation becomes the only way to transfer quantum information perfectly from one place to another without measuring it. There's something wonderful about exploring the limits of what's possible, about asking questions like, can we teleport, even when the answer is mostly no? Because in searching for the answer, we discover so many other things. We learn about the quantum world and its strange, beautiful rules. We invent new technologies that change the world in ways we never expected. We push the boundaries of human knowledge and understanding. The dream of teleportation has led us to quantum computers that can solve problems regular computers never could. It's led us to communication systems that are perfectly secure. It's led us to discoveries about the fundamental nature of reality, about how particles can be connected across space, about how information works at the deepest level. Even if we never teleport a person, even if human teleportation remains forever impossible, the journey toward that impossible goal has been worth taking. Because science isn't just about achieving the things we set out to achieve, it's about learning, discovering, and understanding. It's about taking ideas that sound like magic and seeing how close we can come to making them real. And who knows, maybe someday, centuries from now, humans will find a way around the obstacles we see today. Maybe they'll discover new physics we don't know about yet. Maybe they'll invent technologies we can't imagine. The history of science is full of things people thought were impossible that later became routine. Flying was impossible until it wasn't. Talking to someone on the other side of the world was impossible until it wasn't. Seeing inside a human body without surgery was impossible until it wasn't. Landing on the moon was impossible until it wasn't. Every generation has its impossibilities, and every generation is proven wrong about at least some of them. So, perhaps human teleportation really will remain impossible forever. Or perhaps it will just remain impossible until someone clever figures it out. We don't know. We can't know. But we can keep asking the question, keep exploring, keep pushing against the boundaries of what's possible. There's also something profound about how quantum teleportation changes the way we think about information itself. For centuries, we thought information was just an abstract concept, something that existed in our minds, or on paper, or in books. But quantum mechanics shows us that information is physical. It's encoded in the states of particles. It follows physical laws. It can't be created or copied arbitrarily. Information, it turns out, is a fundamental part of the universe, just as real as matter and energy. Some physicists even think that information might be more fundamental than matter and energy, that the physical world might ultimately be made of information rather than stuff. This idea, sometimes called it from bit by physicist John Wheeler, suggests that reality itself might be a kind of information processing. Every particle, every atom, every star is processing quantum information, transforming input states into output states according to the laws of physics. From this perspective, the universe is like a giant quantum computer, constantly calculating, constantly evolving, constantly processing information. And we, with our consciousness and our thoughts, are patterns of information processing within this larger cosmic computation. Quantum teleportation fits beautifully into this view. If information is fundamental, then being able to move information from one place to another without it traveling through the space in between isn't just a neat trick. It's telling us something deep about the nature of reality. It's showing us that space, the distance between things, might not be as fundamental as we thought. What's really fundamental is the information, the quantum states, the patterns. And these patterns can be connected across space through entanglement in ways that seem to defy our everyday intuitions about how the world works. Some physicists have even proposed that space-time itself, the fabric of the universe that Einstein showed us is curved by gravity, might emerge from quantum entanglement. This idea, explored by physicists like Juan Maldacena and Leonard Susskind, suggests that the connections between entangled particles might actually create the geometric structure of space. In this view, space isn't a fundamental thing that exists on its own. Instead, it's something that emerges from the pattern of entanglement between quantum particles. If this is true, then quantum teleportation isn't just moving information through space. It's using the fundamental connections that create space in the first place. These ideas are still very speculative, still being explored and debated by physicists. But they show how quantum teleportation connects to some of the deepest questions in physics. Questions about what space and time really are. Questions about how quantum mechanics and gravity fit together. Questions about the ultimate nature of reality. By studying quantum teleportation, by learning how to move quantum information from one place to another, we're not just developing new technology, we're probing the foundations of existence itself. There's something humbling about this, about realizing that a simple question, can we teleport, leads us into these profound territories. It reminds us that science isn't just about building useful things, although that's certainly important. Science is also about understanding, about asking questions, about following those questions wherever they lead, even when they lead us to ideas that challenge everything we thought we knew. The quantum world has challenged us in this way before. When scientists first discovered quantum mechanics, they had to accept that the universe was probabilistic at its core, that you couldn't predict everything with certainty, even in principle. They had to accept that measurement changes reality, that observation isn't passive but active. They had to accept that particles could be in multiple states at once, that reality at the quantum level is fuzzy and uncertain. These ideas were hard to accept, and some scientists struggled with them for their entire lives. Entanglement added another layer of strangeness. The idea that particles could be connected across space, that measuring one could instantly affect another light years away, seemed to violate everything physics had established about how the world works. But experiments proved it was true. The universe really does work this way. And now quantum teleportation adds yet another layer, showing us that information itself has properties we never suspected, that it can be moved in ways that seem impossible. Each generation of physicists has had to expand their understanding, to accept ideas that seemed impossible at first. And each time, the universe has turned out to be stranger and more wonderful than anyone imagined. Who knows what the next generation will discover? What new impossibilities will turn out to be real? What new questions will lead to new understanding? And now, as our journey through the science of teleportation comes to a gentle close, let's think about where we've been. We started with a simple question and followed it down into the quantum world, that strange realm of tiny particles where the rules are different and the impossible becomes merely unlikely. We learned about entanglement, that spooky connection that Einstein doubted but that turned out to be real. We learned about how quantum information can be moved from one place to another, not by traveling through space, but by using the deep connections between entangled particles. We learned about the experiments that have made quantum teleportation real, sending quantum states across cities, across countries, even up to satellites in space. We also learned about the limits, about why teleporting a person or even a single cell remains impossibly difficult, about the uncertainty principle and decoherence, and the unimaginable amount of information that would need to be measured and transmitted, about the philosophical questions we would need to answer, even if the technical problems were solved. But we also learned that sometimes the journey is more important than the destination, that asking whether teleportation is possible has led us to quantum computers, quantum networks, and a deeper understanding of reality itself. That even if human teleportation never happens, the dream of it has already changed the world. Science is patient. It moves. Slowly, one careful step at a time. It asks questions and waits for answers. It tries things and learns from its failures. It builds on the work of everyone who came before, adding one more small piece to our understanding of how the universe works. And the universe, it turns out, is strange and surprising and more wonderful than we ever imagined. Particles that are in two places at once, particles that are connected across space, information that can be moved without traveling. These aren't fantasies or fairy tales. They're real. They're true. They're happening right now in laboratories around the world. But the universe also has its rules, its limits, its boundaries that cannot be crossed. Faster than light travel remains impossible. Perfect knowledge of quantum states remains impossible. Creating matter from nothing remains impossible. And teleporting a person, at least as far as we understand physics today, remains so difficult that it might as well be impossible. But impossible is a funny word. It means different things in different contexts. There are things that are impossible because they break the laws of physics, like traveling faster than light. And there are things that are impossible because they're too hard, too complicated, too expensive, but not actually forbidden by any fundamental rule. Human teleportation might fall into this second category. Not forbidden, just unimaginably difficult. And that means that someday, maybe in 100 years, or 1,000 years, or 10,000 years, someone might figure it out. Or maybe not. Maybe human teleportation will remain forever in the realm of science fiction, a beautiful dream that physics simply won't allow. Either way, we've learned something. We've taken a journey together through one of the most fascinating questions in science. We've seen what's possible and what isn't, what's real and what's imagined, what works and what doesn't. Think about how much we've discovered in just the last few decades. 100 years ago, we didn't even know atoms existed. 70 years ago, we didn't understand entanglement. 30 years ago, quantum teleportation was just an idea on paper. And now, today, it's real. Scientists around the world are teleporting quantum states every day. They're building quantum computers. They're creating quantum networks. They're pushing the boundaries of what's possible, one experiment at a time. The journey from impossible to possible is always longer than we expect, but shorter than we fear. Technologies that seem like pure fantasy often become reality through the patient, careful work of many scientists over many years. Each generation builds on what the previous generation discovered. Each experiment teaches us something new. Each failure shows us what doesn't work, which is just as important as knowing what does work. And who knows what the scientists of the future will discover? Maybe there are forms of physics we don't know about yet. Maybe there are ways around the obstacles we see today. Maybe the limitations that seem absolute to us will turn out to be just technological challenges that clever people can solve. Or maybe human teleportation really will remain forever impossible, forever in the realm of dreams and stories. But that's okay too, because the value of a question isn't always in whether we can answer yes or no. Sometimes the value is in the journey we take while exploring the question, in what we learn along the way, in how the question changes us and changes our understanding of the world. The science of teleportation has taught us so much about the quantum world, about entanglement, about the nature of information, about the limits of what's knowable and what's possible. It's given us new technologies that are already changing the world. It's given us new ways of thinking about reality itself. And it's reminded us that the universe is stranger, more wonderful, more full of surprises than we ever imagined. There's a certain comfort in knowing that mysteries still exist, that there are still questions we can't answer, puzzles we can't solve, dreams that might remain dreams. It means the universe hasn't given up all its secrets yet. It means there's still more to discover, more to understand, more to wonder about. It means that children being born today will grow up in a world with questions to explore, mysteries to investigate, and dreams to chase. The history of science is full of impossible things that became possible. People once thought it was impossible to fly. The idea of heavier-than-air flight seemed to violate common sense. How could something made of metal possibly stay in the air? But the Wright brothers and others figured it out. They studied birds. They experimented with wing shapes. They built wind tunnels and tested different designs. And in 1903, they achieved powered flight. Today, millions of people fly every single day, and we barely think about how remarkable it is. People once thought it was impossible to see inside the human body without surgery. But then, Wilhelm Röntgen discovered X-rays in 1895, quite by accident, while experimenting with cathode rays. Within months, doctors were using X-rays to see broken bones. Today, we have not just X-rays, but CT scans, MRI machines, ultrasound, and other imaging technologies that let doctors see inside the body in incredible detail, all without making a single cut. People once thought it was impossible to communicate over long distances without physical wires. But then Guglielmo Marconi and others developed radio technology in the late 1800s. Then came television, satellite communication, cell phones, and now the internet. We can talk to someone on the other side of the world instantly, see their face on a screen, share files, send videos, all wirelessly through the air. This would have seemed like pure magic to someone living 200 years ago. People once thought splitting the atom was impossible, that atoms were the smallest units of matter and couldn't be divided. But scientists in the early 1900s showed that atoms are made of smaller particles. Then they learned to split atoms, releasing enormous energy. This led to nuclear power and nuclear weapons, technologies that have shaped the modern world in profound ways, for better and worse. People once thought landing on the moon was impossible. The moon is 250,000 miles away. How could humans possibly travel that far and return safely? But scientists and engineers worked on the problem. They built bigger rockets. They developed new materials. They calculated orbits and trajectories. They solved problem after problem. And in 1969, Neil Armstrong and Buzz Aldrin walked on the moon while Michael Collins orbited overhead. Humans had left Earth and walked on another world. The impossible had become reality. So when we say human teleportation is impossible, we need to be careful about what we mean. Do we mean it's impossible according to the laws of physics? Or do we mean it's impossible with current technology? Or do we mean it's impractical, so difficult and expensive that it will never make sense to do it, even if we technically could? These are different kinds of impossible, and they have different implications for the future. Quantum teleportation, the real kind that moves information instead of matter, was considered impossible until it wasn't. It was just theory until 1997, when scientists made it work. Now it's routine. Labs around the world teleport quantum states every day. What seemed impossible has become ordinary, at least for scientists working in quantum laboratories. Maybe human teleportation really is fundamentally impossible, forbidden by the laws of physics in ways we can't get around. Maybe the obstacles we see today, like the uncertainty principle and decoherence and energy requirements, really are insurmountable. Or maybe, centuries from now, scientists will look back at our concerns and smile, the way we smile at people who thought flying was impossible. Maybe they'll have found ways around the problems we see as absolute. Maybe they'll have discovered new physics that we can't even imagine yet. We don't know. We can't know. The future is uncertain, always. But what we can know is that asking the question, exploring the possibilities, following the science wherever it leads, is always worthwhile. Because even if we never achieve the goal, we learn so much along the way. And that learning, that growing understanding of how the universe works, is valuable in itself. And now it's time to rest. Time to let these ideas settle gently in your mind, like leaves falling on a quiet pond. You don't need to understand every detail. You don't need to remember every fact. Just let the wonder of it all wash over you. The wonder of entanglement and quantum states and particles that are connected across the universe. The quantum world is still out there, still spinning, still entangled, still following its strange and beautiful rules. And somewhere, in a laboratory, a scientist is teleporting another quantum state from one particle to another, adding one more small piece to our understanding of what's possible. But that work can wait until morning. Tonight is for rest, for peace, for letting go of questions and simply being. You have learned enough. You have wondered enough. You have done enough for today. Close your eyes now. Let your breathing slow and deepen. Feel the weight of your body, solid and real and wonderfully unteleported. You are here, in this moment, in this place, and that is exactly where you need to be. The universe will still be strange and wonderful in the morning. The quantum world will still be there, waiting to surprise us with its mysteries. The question of whether teleportation is possible will still be there, beckoning to curious minds. But for now, all of that can rest. Sleep peacefully, dream softly, and know that in this vast, surprising, endlessly fascinating universe, you are exactly where you belong. Right here, right now, present and peaceful and perfectly yourself. The particles can stay entangled. The photons can keep their quantum states. The laboratories can continue their experiments. But you, dear listener, you can simply be, simply rest, simply let go. Good night. Sleep well, and may your dreams take you wherever you wish to go, faster than light, beyond the rules of physics, to all the impossible places that exist in the quiet spaces between waking and sleeping. You have done enough for today. Close your eyes, rest, and dream. The end.